Hi, it's already the last theory lesson of Math 3, and in this lesson we're going to look at binary trees and other sorts of trees, and we're going to order them in some ways, and as last we're going to look at the Huffman's algorithm for coding a big amount of data in an efficient way. Enjoy this last lesson. Okay, what is a binary tree? In fact, that's just an ordinary tree, but only with, for every vertex, maximum 2 edges. And so we have a top, and we can go to the left and to the right, but not somewhere in the middle. So a binary only has 2 edges maximum for every vertex in the tree. One is allowed, so this could have an extra edge I, and that's also a binary tree, but maximum 2. We have some naming conventions. These are children of the root A, and we call B the left child and C the right child. And D is the left child of B, E is the left child of C, etc. You can also talk about parents if we have a child and we also have a parent. So for instance, B is the parent of D, and a parent can have 0, 1 or 2 children. If we have this binary tree, then it's normal we go from the top to the bottom, so we don't draw the arrows. Well, we keep it nice and clean. So in fact all these arrows are just omitted, but we have an agreement. If we see a tree, we go from the top to the bottom and not the other way around. In a tree we can also talk about subtrees, just like we talk about subgraphs, and basically it just means exactly the same. So for instance, this blue area here is a subtree of the original tree. If we look at B itself, we can also have a left subtree. That's this one. That has to be taken into the complete subtree, including all leaves. And of course there is nothing there, so there is no right subtree. We can also talk about levels in a binary tree, and then we agree that the first one, so the root of this tree, is called level 0. So level 0, 1, 2, 3. Just an agreement. And of course, because it's a binary tree, then every level has a maximum number of nodes. And so the root can only be 1 because it's a rooted tree, and level 1 has a maximum, of course, of 2, because A can have a left one and a right one, and it also can have none. So A is always 1, and level 1 has maximum 2 nodes, maximum, so that's 2 to the power of 0. And you can imagine if we continue, level 2 has maximum 4 nodes, because I could have added here one. So let's call it x. So on this one, 2 to the power of 2, etc. So depending on the level number, we have a maximum number of nodes at that level. If we visit the nodes, we can have several ways to do this. So let's first look at the pre-order. That's the one we already know. You can compare it with the depth first search. Pre-order means if we visit a root, we immediately process it. So we do A, B, D, G. Okay, that was what we could do depth in the first depth iteration. Then we have to go back, and we already done D, so we don't do it again, and we try to go depth again. H, okay, back, B, back, C is processed now, E is processed, F, and we return. So in pre-order we visit A, B, D, G, H, and then we go to B already done, I already done, C, E, F. And so in fact that is equivalent with a depth first search. Okay, let me erase this. I'll first do the post order and then we'll continue with the in order. If we look at the post order, then in fact we go again with the depth first search, but now we don't process them at our first arrival there, but we process them as last as possible, post order. So we go down again, depth first. Okay. If we now move around G, then we know we can't go back to, we will not visit G anymore, so G has to be there in a post order. We go to H, oh dear, last time we are here, so H. Then last time we are in D, last time we are in B. Okay, but now we can again go down around E, last time we visit E. Okay, last time we visit F, C for the last time, and then finally A. So the post order in fact is again a depth first, but we only order them, we process them the last time we see them. So let's look at the in order visit. So the in order is something in the middle, huh? So not the first time, not the last time, but the second time we visit a node. So we start at A, we go to the left, we go to the left, we go to the left, and then at G we try to go to the left. But there is no left tree, so we go back and we have the second visit. So G. Okay, we try to go to the right, no right, so we go up. Second visit. We go to H, we go to the left, nothing there, so we go back again. Second visit. Go to the right, nothing there, and go back. Then we are for the second time in B. We go to the right, nothing there, and we go back. Then we go to A. Okay, second time visit. We go to C. We go to E, we go to, the left, nothing there, we go back, E, we go to the right, nothing there, we go to C, second visit, we go to F, go to the left, nothing there, so second visit F, we go to the right, nothing there, and we go back, and we end in A. So the in order is the second time we visited. Implementation of these visiting methods can be done with the help of a recursive program. It's a very elegant program we can make. Recursive means that you define a function, and in this function the function you're making is called again. That's the meaning of recursive. So the function of a pre-order visit would be step 1, start with the root. Okay, that's A. And then twice the recursive method is called again. So pre-order this tree and pre-order that tree. Okay, let's do that. So we pre-order this tree. And then we have to follow the prescription again. Start with the root. That's B. Then pre-order the left tree, and the right tree is not there, huh? So we can't do that anymore. Okay, let's do it. Pre-order this tree. So D. And then you can already see, okay, now we have to do G and H. And now we have done this visit of the left subtrees. Then we can continue with the right subtrees. So pre-order this tree, so that means visit the root, and then pre-order, and those are only leaves, so there's nothing left to do. So with the recursive definition, we just follow the prescription, we do the root, pre-order. Okay, we do the root, pre-order, etc. So let's check that again with our intuitive way here. So we start at the root, A, we go to B, depth first here, so D, G, okay, backtrack, H, great, we already did this one, we did this one, C, E, and F. And so with this recursive definition, and you can, I don't know whether you already done recursive programming in your programming classes, but as soon as you get there, remember this one, because it's really a nice algorithm to implement in a recursive way. For all the others, we also can define them with recursive definitions. So if we look at the in order, then the recursive definition would be, okay, we visit the left subtree, we process the root, and we visit. So we are in order. Now let's just in order the total tree. Now let's just call it with the root. What happens then? Then we visit the left tree. So we do in order B. Okay, and then we process the root. So then the root is processed. So that's A. And we do in order the right tree, C. Yeah? Well, if we look at in order B, you can imagine that's exactly the same. So in order B, we go down, D, we process, and we go in order G, in order H, we process. So in fact, in order E, in order B, in order D, now we can't do anything anymore, so now we process the root, that would be G, then we go back, we do D, process H, process B, process A, that's this process the root thing, and we go to the right one, so C, E, F, and that's it. And so in the in-order recursive definitions, we just go first to the left, then process, then to the right. And that goes for everything. So if we are in B, first to the left, then the right, then process, etc. And you can imagine how the recursive definition of the post order will look like. And so that is visit the left tree, visit the right tree, then process. And so then the root processing is last. So in fact what you see is that this process the root in fact falls down the ordering of your actions. So in the pre-order we started with process the root, in the in order we did it as the second action, and in the post order we do it as the last action. So no big differences. For a non-binary tree like this one, because here for instance the root has 3 leaves, has 3 edges, we can also do the pre-order and the post-order traversal. We can't do the in-order traversal. And then pre and post are just as we are used to it. So we go depth first, and in the pre-order we process immediately. Etc. And in the post order we process later on, the last time we arrive. And so I will give it a different color. So in the post order we follow the blue line, and then this one is processed one first, then this one, etc. So pre-order, post-order traversal, it works exactly the same as with the binary tree. No problem. Last issue in this Math 3 course is the Huffman's coding algorithm. And in this case the coding algorithm is not to encrypt data, but to try to small it down. And so if we have big amounts of data, it is nice if we can code it a little bit more efficient, that we don't need so many bytes to represent it. And a very famous one is the Huffman's algorithm to do this. For instance, if we look at the ASCII table, then you could just code it. And normally the A is with a 7-bit and the B is with a 7-bit, etc. And that means that all characters are coded with 7 bits. So also the Q and the X and characters that don't happen that much, that don't occur that often. So it's not a very efficient way of coding. So all chars are coded with equally length. So for instance, if we look at the sentence eat a banana, and then of course in this case we have a lot of A's. So this A's happens very often, and for instance the B only once, but for all elements we use the same amount of bits. And so this one here is an A, and this one is an A, this one is an A, that one, and this one. So for all those A's we use the same amount of bits. That's not efficient. So for instance we could say, okay, I only have 6 different characters, so to code 6 difference I only need 3 bits, and then in fact I even have 2 spare ones, because with 3 bits I can code 8 different characters. So that would already be much more efficient. But it even gets more efficient if we can code with different lengths. So if a char happens often, then we give that a smaller size, and a char that doesn't happen so often, we give that a longer size. So for instance, if we look at this eat a banana thing, then the A happens most. Let's just fill it. So we should give the A the shortest code. And then if we look very simple, we could say, okay, then the A becomes 0, and then we have one which happens twice, so that's the space and the N. So we gave those codes 0, 0 and 1, etc. However, you immediately see a problem, because how can a computer tell whether we're coding an A if he finds a 0, or if he's coding a space when he starts with a 0? They are prefix of each other, so that's not allowed. If we have this code, then if we start at 0, yeah, a computer could say, okay, that's an A, and then we get a 1, and then he would say, okay, that's an N and an A, and you see what happens. We only get A's and N's in this message. So if we do this kind of a separate length coding, then we can't have one element being a prefix of another element. That's not good. We can try to do something else, and now our theory about trees comes in handy. If we make a tree which has the same amount of leaves as the amount of chars we want to code. So in this case, eat a banana had 6. So 1, 2, 3, 4, 5, 6. And then we're quite sure, because it's a binary tree, that every leaf can only be found in one specific way. So if we take 0, and this one would be the A of course, that's the only route to this A, because the other one starts with 1, and then we can choose. We can go to the left with a 0, or we can go straight on. And in this way we have unique codes for every element. And the idea is, of course, that we code the highest frequency in the shortest, in the closest to the root leaves. So, for instance, if we would decode this strange bit array, then we have 1, 1, 1, 1, 0. So this is the first element, that's a B. Then we have 1, 1, 1, 0, 0. Okay, that's this one. That would be an A. Now we have a nice short one, 0. That's an A. Sorry, the previous one was an E. And then the last one, 1, 1, 1, 0, 1. That would be a T. So in this way, there can't be any problem. Every leaf is coded very specifically, and no char is the prefix of another one. If we then look whether it's really efficient, we have a nice way of measuring it. We can calculate the weight of the tree, and it's just adding up all the bits. So how many bits do I use to code one specific sentence? So let's try this tree out with the original sentence, eat a banana. Now, if we look at eat a banana, then this would be the coded message. Now you can trust me that that's done correctly here. Well, let's just check. E, A, and then 11101. It's T, well, etc. And if we do the complete sentence, we just have to calculate the number of bits, and that's the weight that this tree will give the sentence eat a banana. And in this case, it's 30 bits. Okay, is this the smallest one, or can we find even better codes? So, for instance, this tree, that also has exactly 6 leaves. So could we optimize our tree so that indeed the code is as small as possible? Well, this one, let's try it out. So eat a banana, so the E would be 10. Then we have the A, that would be 3 zeros. Then we have the T, that would be 110. A space 01, A 000, a space 01, the B gives us 111, A 000, the N gives us 001, and the A would give us 000, 001, 000. So this tree, as we would have expected, because the highest frequency is a 3-bit representation, is more expensive. So the weight of this tree would be 5, 10, 15, 21, 24, 27, 30, 33. And we would have expected this tree to be bigger than the previous one, because we tried already to give A the shortest leaf. Okay, but how can we be sure what is the shortest, what is the best tree for a specific message? And here we can use the Huffman code. And the Huffman code, you see here the algorithm of it. In fact, it says just do the weights in increasing order. And then for every 2 weights, the 2 smallest, add them together and replace the sum with the 2 smallest weights. And at the end, when there are only, in fact, 1 left, 1 total sum, we try to build the weighted tree upside down. Again, this looks really complicated, but if I will give you an example, you will see that it's really ingenious. So let's look at this example. So let's say we have the following frequencies, so 22 times an A and 30 times an S, etc. Then what Huffman's algorithm says is, we'll first order them, so from 1, 5, 7, 8, etc. Then in the next step, we are going to combine the 2 smallest elements. So 1 and 5 are combined into 6. And so here we have this adding. And we'll repeat it. So we'll combine the 2 smallest one, that's 6 and 7, and that becomes 18. But keep in mind, we keep the list ordered. And so the 1 and 5, 6 is still the first one, but 6, 7 is 13, that's larger than 8. And so the 8 stays up front. Okay, then we combine 8 and 13, so that'll become 21, but this 13 is smaller. Okay, we repeat again, 13 and 21 is this 34, and then the last step is 56. And now we are going to build the tree upside down. So we start with 56. And then this 56 consists of 2 nodes, 22 and 34. Okay, let's make them. Then again, the next step, this 34 consists of 13 and 21. Let's build it. Then 21 consists of 8 and 13. These two. Then 30 is 6 and 7. These two. And then the last one, 6, is built out of 1 and 5. And now you see that all the leaves have the original frequencies. So 22 is the one with the smallest length. That's the highest frequency. Then we have the second one is 13, the second highest frequency. Then we have 8, we have 7, and 5 and 1 are the ones at the end. So with the help of this algorithm, you really build up very nicely a very efficient tree where all frequencies are divided justly. And the weight of this tree is, in this situation, I don't want to add it, 130. I trust them. Okay, so let's try to build a Huffman tree for our original message, eat a banana. And there we have the frequencies 1, 5, 1, 2, 1, 2. So the frequency 1, 1, 1, 2, 2, 5 in the ordered version. Okay, we combine the first two ones. That would give us 2, but there is still one left in front of it. 2, 2, 5. Then we combine 1 and 2, that becomes 3, and there are 2 2's in front of it. 2, 2, 3, 5. Okay, the 2 2's become 4 with the 3 and 5 in front of it. The 3, 4 becomes 7 with the 5 in front of it, and we end up with 12. So if we build a tree, we start with 12, and we have 5 and 7. 7 was made out of 3 and 4. 4 was made out of 2 and 2. And then this 3 was made out of 1 and 2. And then we still have this 2 left, which is 1 and 1. And so we have this combination here, then the 1, 2 together, that's 3, and we have a nice elegant tree. Let's check the amount of leaves. We should have 6, 1, 2, 3, 4, 5, 6. Okay, and by building this tree, we definitely have the most efficient way to code eat a banana. So the only thing now we have to do is add the chars to the frequencies used, and then we're done. And let's calculate again the eat a banana, whether it's indeed more efficient. If you have plenty of time, you can check this, but trust me, this is correct. And then we have 28 bits for this message, so it's shorter. Okay, lovely. And then you would say, well, that's not a big difference. We have 30 and 32, I think, and now 28. But can you imagine that we have something like this? 4 gigabytes. And look how much green there is. And then we have the red and blue areas, which are quite frequent happening. So if we would code this one with, for instance, green being the smallest code, then it would give you a very high change of the amount of bytes used to code such an image. Okay, that was it. So still exercises of lesson 5 to do. There will be a mock exam in lesson 6, but I hope you enjoyed. I definitely did. The graph theory with all its different algorithms and different codes is quite interesting. On the internet and in the book you can find many more examples of coding algorithms and graph theory. Okay, so for now, goodbye, and hope to see you again with the mock exam.